Hi, welcome to the Calculus 1 lecture series. And we are in the unit number 4, talk about the integrals. This is the lecture number 27. And this is our third videos for this unit. And in this video, we're going to talk about the fundamental theory of the calculus. Since, we have been talking about the derivative, and we have talked about the antiderivative and the definite integrals. So in here, we're going to talk about what is the fundamental theory of the calculus. Okay, so now let's go ahead, go to start our lecture notes here. All right, so the fundamental theory of the calculus. So basically, this theory tells us how do we link the derivative and the integration together here. All right, so the fundamental theory of the calculus, or you will see some book, they use the abbreviations FTC, right? Fundamental theory of the calculus. Okay, so we have two parts, all right? So the part one, sometimes we say fundamental theory of the calculus number 1 here. So what is the first part here? The first part here, they tell you, let me write it, all right? So we say if f is a continuous, okay, on this interval on the AB, and the g is another function, and the g is defined by, okay, so here we say the gx is equal to, you take the definite integral of the f of x, and from the a, then x is anything in AB. So here, this is a to the x here, right? And the f of t dt here. Okay, and then we said g is a continuous. Gx is a continuous. All right, so on the AB, okay, and g prime x will just be equal to f of x for all the x in AB here. Okay, so there are a few key things we need to be careful. See here. So the first things here, we said f has to be a continuous on the ABs here. And then, the other things we need to pay attention is here. So this upper bound is a variable. So it's x here. So it's from the a to x. So because every time you from the a to x, then you defined a function gx here, right? And be very careful here. Then here, I change the variable. I said, instead of code x, I code ft. So that's why I take the integration for the t. And the reason why I change that, so it's because my boundaries here is x. I cannot integrate here and with boundary variables here. All right. So that's why I changed my variable, but I really did not change it. So we did not change like the what is the function form. So for example, like here, the fx equal to x squared plus 3x plus 1. All right. So when I said f of t, that means my function form still here is t squared plus 3t plus 1. So now I can integrate right from the a to x. Now I have a t squared plus 3t plus 1. Then to the dt's here is because of what I'm integrating and what my boundary cannot be the same. So I cannot have a dx here. I cannot change dx and have the variable on the x here. Okay, so this is the first thing. So then the second thing here, we need to be very careful. Then they said after you do that, then gx will be a continuous function. here, right? So gx is going to continuous function. And then this is the most important part. And then they said, if you want to take the derivative of the gx, so if you want to take the derivative of the gx, because gx and f of x, so f of x you integrate to become gx. So that's why they say the first fundamental theory of the g prime, that means if you want to take the derivative of gx, but gx is the integration of the f of x, right? So it's really you just similar, like you put the x back to the, so will just be the function f of x here. You see that? All right. So this is a very, very important results, right? Because sometimes I don't even, maybe it's very difficult to take this integration. Then you use the fundamental if you want to take the derivative. So let's basically tell you what the derivative and integration, they cancel that out, right? So you take the derivative here, but because this is the integration of f of t, so it's basically you just cancel that out. Okay, so now let's take a look at the second one. So what is the second fundamental series of calculus? This is FTC. This is the second fundamental series of the calculus. So these ones tell you here, let's write it out, and then we're going to highlight a few things is important, right? So we say if f is continuous, so it's on AB. So if f is a continuous function and AB, and we said I define the new function capital F of x is an antiderivative. So in the previous unit, the last video in the previous unit, we talk about the antiderivative. That means whatever you take the derivative of the capital F of x will give you the little f of x, right? So if the capital F of x is antiderivative of the little f of x, so what do they say here? They say, now if you integrate f of the x from the a to b, then you can write it. So it will be the antiderivative. So will be the antiderivative of the FB minus the antiderivative of the FA. Or sometimes people like put it like in this way. So you can see this notation. So this find the f of x, and then you have a upper bound and the lower bound here. Okay, so also this is the, it's a super important results, right? Let's kind of now based on the fundamental theory of the calculus, then the second part, then we will really be able to, by using the antiderivative concept and the second part of the fundamental theory of the calculus, I can really figure out what is the exact values here. Of course, here, the key things here is f has to be a continuous, right? All right, so now let's try to practice this two very important concept. Okay, so now the first things here, okay, let's take a look at this one. So this one is say the h of x is you take the integration of the square roots of the x, and then your upper bound here is what is x here, right? So then let's say, what is the derivative of hx? Okay, h of x here is the integration of here. Then you take the integration, then you take the derivative. So what is the value of this one? Would just be the same, like you put the x into your function. So it will just be what? Square roots of x, right? Because like we said, integration, hx is you integrate. After you integrate, then you take the derivative, right? So that's why it will just be same, like you put the x back to your f function, and that will be the h prime x. So it's a lot easier. You don't need to physically, you don't need to physically kind of take the integrations and then do that. All right. Now the second problem here is if f of x is a continuous on AB, all right, for all the x in AB, then let's say, so this one's basically just tell you, okay, you integrate, all right, so you integrate this ones here, right, you integrate this one, and now what you do here, you integrate, then you take the derivative, right? So like we said, the fundamental theory of calculus is kind of like telling you the integration and the derivative is kind of like they cancel each other out. So what is this answers here? So you integrate from the a to x, the f of t, then you take it into derivative. So basically this answer will just be f of x. All right. Okay, and so now let's take a look. So this is based on the fundamental theory of what? Fundamental theory of the first part, right? Okay, now let's take a look. It said if f prime x is continuous on the ABs here, if f prime x here, right? Be careful, see here, the notations here, this is f prime x is continuous on AB. So they want to find what is this value here. Okay, so if f prime x is continuous on the AB, so that means the f of x, what is f of x? F of x is the antiderivative. So it's the antiderivative of what? Is the antiderivative of the f prime x, right? Okay, so let's take a look at what we have here. So this is f of a, and then based on the, the fundamental theory of the calculus, fundamental theory of calculus part 2. So this will be equal to the antiderivatives, right? So the antiderivative, so it will be f upper bound, so will be f of x minus f of a, right? So here, color coding here. So this part here going to change to this part, right? Why? It's because of what? So from here to here, this is because of the fundamental theory of the calculus part 2. Now FA cancel. So what is your final answer? It's f of x. Okay, and so then the part C, they tell you, say, hey, we did this two part. What does the part A and part B see here? So, okay, so part A, okay, so take a look. You take integration, then you take the derivative, then will become the self. So basically, part A said differentiation. What will undo the integration part. Right? So that's what is part A say, right? You integrate, then you take it in derivative. So that's why the differentiation will undo the integration part. So give you the f of x here. Okay. All right. Then the part B is here. What is the part B? So it's go backward, right? So part B says what? The integration will undo what? Taking a derivative. Okay, so that's what is the, so because here this is derivatives, right? So this is the, this is the derivatives inside, right? So that's why the integration will be undo the derivative part. All right, so now let's summarize here. So what do they you combine these two, so what do we have? So we said integrations and differentiation. Okay, are what? Inverse process. Right? So the people finally identified, they said, oh, you know, that is what, right? So it's the inverse process to each other. So the integration will undo the derivative, and the derivative will undo the integration. Okay, so now let's take a look here, right? So now the number 3 is here. Let's try to evaluate. This is definitely integral. So we say we finally be able to evaluate this definite integrals here. Okay, so let's take a look at this is 1 minus x, right? So I want to evaluate this. I need to find what is the antiderivative, right? So 1 minus x. So what is 1 is x to the 0 power. This is x to the 1 power, right? So what is the antiderivative of this one? Will be x minus x squared over 2, right? Then plus what? Plus c here, right? So this will be the antiderivative. So this is my f of x, right? Correct? Okay, so now based on the fundamental theory of the calculus, you know, the calculus is that part 2, so we know this will be equal to x minus x squared over 2 plus c, and then you have the upper bound and the lower bound. Then you substitute your upper bound here. So let me color code this one. So upper bound will be y minus 1/2 plus c, right? Then minus. So this part is your what? This part is your upper bound. Okay, then minus, you put the values here. So this is 0 minus 0 plus c. And let me color code that. This is your lower bound, right? So you substitute the function to your lower bound. As you can see in here, you know, the antiderivative, the c and the c will always cancel, right? So this is 1/2 minus 0. So what is the final answers here? This is 1/2. Okay, so because of the antiderivative, this is c constant, you know, when you substitute, the c always there. So because you use the top boundary minus lower boundary, c and c will cancel, right? So when we try to do it, we don't really need to write c anymore. So let's take a look. So for this one here, right? So for this function, this is ex, right? So let's take a look at what is the antiderivative of this one. So we know the ex, the antiderivative is very good, right? So it's ex plus c. But because we know when we substitute the upper bound and the lower bound, the c going to cancel. So I don't really need to write the c anymore, right? So I can just say this one will be equal to the ex, then the upper bound and the lower bound, right? Because you write c or not, it's going to cancel, and so I just can, you know, I can just solve it without writing. So this will be the e to the 1 minus e to the -1, right? So this will be just the e minus 1 over e. If you want to simplify, you can simplify, or you can leave like this. Okay, now the next one is here. This is 1 over x squared. Okay, so 1 over x squared, we want to find the antiderivative. So this is x to the what? -2, right? So now I want to find the antiderivative, will just be -2 plus 1 will be what? -1, and -2 plus 1 is -1. You know, when we try to do those type of problem, the main things here is just you need to be careful about this plus minus signs, right? So this is my antiderivative. Like I say, I don't really need to write the c anymore, so you will have a -1 over x. And then you have 3 and you have 1. All right, so be very careful, right? So now you substitute the 3, so this is -1/3. Then minus, you substitute 1 is -1, correct? Right, so there is negative, negative is a positive. So what is your answer? Is 2/3 here, okay? Okay, So now for this province here, the next ones here, you say, hey, they are looking the exact same questions. Oh boy. Let me erase this. Okay, so you say, hey, they are exactly look the same question. Okay, so in this ones here, you know, because the interderivative is extra -1, -1s, right? These ones here, you know, we can do like this. So if you say, oh, okay, so the interderivative is 1 negative x, and there's 1 and -1. Is this correct? Is this correct? No, this is not correct. Why this is not correct? Because if you look at these functions here, right? This function is not defined. It's not defined at 0, right? So I know this function is not continuous at 0. So it's a violate. Take a look at our definition. You know, the very important has to be continuous, but this one is not. So it's violate our assumption. So I cannot use the fundamental theory of calculus part 2. Now, how do I do it? We're going to talk about in the later videos, how do we deal with this one? So, but for here, this one we know I can apply the fundamental theory of the part 2, but I do have a different method I can use it. All right. Okay. So now, number 4 is here, right? And so we said, you know, the x between, right, the 1 and the 3, right? And then the x here is any number in there. So I want to find the h prime x. Okay, so what's that means here? Okay, so let's take a look here, right? So I know the hx is the areas, right? So, well, also, okay, so I know the hx here by the definition of the area. So the hx is what? Is 1 to what? 1 to the x's, right? I try to find the area. That's what we define as definite integrals here. Now, what is the function here? The function is t to the square dt. Correct? All right. So now I want to find h prime x. Oh, so this one is integration. Then I'm taking the derivative, so we know what happens here. It cancel out, right? So h prime x will just be you replace you replace this value to your functions, right? So that's why you get what is the final answer? X squared here. Why here? This is the fundamental series of what? Part 1 here. Okay, it's very important, right? So we talk about their inverse processing. So the derivative will cancel the integration. So here's the derivative. So that's why this integration cancel. You just bring the values here. Okay, now let's take a look at this one. See here, the last 3 problems here. Let's say here, how do I find the derivative of the functions? Okay, so here gx here. All right, so take a look at this one. See here. This one, this is x, right? We know the derivative and the integration, they cancel each other out. So if I want to find the g prime x, because the gx is the integration, so g prime will just cancel that out. So what is the answer? You just place the x into your function. So it will be x minus x squared to the 8th, right? Pretty straightforward. Okay, now let's take a look at this one, part C here. This one's here. It's a f of x. F of x. Wow, now here, this is x over 2, t3 sine t. Whoa, how do I do this one? Now we say, the fundamental theory tells us, right? So this x has to be on the top, right? So this x has to be on the top. So how do I do that? Then we say, oh, from the previous I know I can switch this boundary, right? So I can switch this to the 2x, right? So also remember when you switch, what happens here? Don't forget the negative signs, right? So you switch from the 2x, then this is t3 sine t dt. Now, if you want to find f prime x here, this negative sign is here. So this is the integration part, right? So this is the integration, and this is the one you have what x here, right? So what you do here, you bring the x down and then replace it. So what is the final answer? Will be the x cube and what? And sine x. Oh, sorry, don't have dx anymore. So the sine x here. Okay, now let's take a look this one here. Okay, this one is very careful here. So you take a look and you see, oh, here, the top here is ex. It's not x here. So if I want to find the derivative of that, so this is similar like we said, because x right now is a functions, right? So, you know, when you derivative, if you have a function, what rule we use? We use what? We use the chain rule, right? Remember that? So for example, if I have x squared plus 2x to the third power, right? So we take the derivative will give you the 3x squared plus 2x to the square. But we say, hey, don't forget, you need to what? You need to chain rule here, right? So it's a 2x plus 2 because they are not the x by itself anymore. It's a function. So here, let's see here. You know, we need to do the same thing. Okay, so the first, we still just place this one into your function. So this is natural log ex, right? You replace it. Then what I need to do, I need to chain rule here, right? Kind of take the derivative, kind of similar like the chain rule concept. So I need to take the derivative of this one. So what is the derivative of this one? Is by itself here, right? So be careful, right? So this is the, you know, here the same, but this really is the derivative, right? This is the derivative of what? Of the ex, right? So now this is my final answer. So this is ex. Then I know the natural log of the e cancel. So this will give you x to the ex. So this will be my final answers here. All right. So this is the one we talk about the fundamental theory of the calculus. So key things to remember. When to use the fundamental theory of the calculus part 2, you know, if it's a continuous function, if the integration domains here, if the integration range is here, right, make the function is discontinuous, and then you cannot use the fundamental theory of the calculus part 2 to do that. Then the second part is the fundamental theory of the calculus 1, and the fundamental series of calculus part 1. So remember, this is very important and very good problems here, right? So that's why we said what happens here is the integration and the differentiation, they are really the inverse process. They undo each other. So that's why from here, you can say, okay, they undo each other. So in here, this part, this one is super important. And it's just like if this is not a single x anymore, you just need to apply the chain rule concept, and then you need to do the derivative of whatever you have here. All right, okay, that's it. Let's see our section for the fundamental theory of calculus. Okay, so I guess we'll talk to you next time, talk about a different topic. How about the indefinite integrals and net change theories here. All right, okay, have a good day. Okay, bye-bye.